So a coil can affect itself. Same idea as mutual inductance, but we're just looking at one coil and how it affects itself. And we call that self-inductance. So just as we had a formula for M for mutual inductance, we use the letter L for self-inductance, and it's based on the number of coils or the number of loops in the coil times its magnetic flux divided by the current through the coil. So we solve for flux, and that's going to be the inductance times the current divided by the number of loops. We'll take the derivative, which is going to make that a function in time. And the only thing that I can take the derivative of is my current. So the current's changing with time. Now I can use Faraday's law. Substitute in. And simplify. So this is our equation for a self-inductance. And so let's see what we can find for a solenoid, because that's the most common coils that we have. So we'll start with the magnetic field in a solenoid. And our flux is just going to be equal to magnetic field times area, and that's just equal to mu times the number of loops in the coil times the current times the inside area of the coil divided by its length. And the inductance is equal to the number of loops times the flux over the current. And if I substitute in here, I get mu times n squared times the area inside the coil divided by its length. So the inductance can be calculated off of the characteristics, the dimensions of the solenoid. This makes them very practical in use.